And if you could please get familiar with the icons on the bottom of your screen. I know that by this time now we are all experts using Zoom, but there is an icon on the bottom that says participants. And at the end of the presentation, if you would like to ask questions to Professor Chen, if you can raise your hand, please. I'm still admitting people, and I guess we are good to go. And if we have more people coming in, I will just admit them as we keep going. Okay. So we are going to start. Professor Chen, can you hear me?
Yes, yes.
Perfect. Can everybody hear Professor Chen? Are we good? Professor Chen, would you like to test your audio, please?
Can everyone hear me? Can you see the slides? Okay, good, good.
Perfect.
Good.
Excellent. Okay. So we are starting now. Welcome to the sounding board. My name is Nelly Hai. I'm the sounding board chair. This is Oceanids 36th year, which is an official support group of the university. The sounding board is a joint effort of the faculty club and Oceanids. Our honorary chair is Crispin Kapolakis, the associate of the chancellor, and our president is Nigella Hilgert. In Oceanics, we raise money for grants and awards for students, support other UCSD events and activities such as the student-run free clinic. We offer many events for our members, and Sounding Board is one of these events. We would like to have you as a member, and I encourage you to. It's only $35 per year. And I'm still admitting people. We are very happy to see you in this our second presentation via Zoom. We are adapting to these new times. And now I would like to introduce to you our speaker, Professor Zheng Chen, Ph.D.
Is it done? Here,
Assistant Professor of the Department of Nanoengineering. His subject will be leveraging reversible chemistry for materials sustainability in energy storage. A little about Professor Zheng. He's the principal investigator of the Laboratory for Sustainable Materials and Energy, LSME. The LSME team is a research group of materials and chemical engineering in the Department of Nanoengineering at the University of California in San Diego. If you could please make sure you're muted as you come in, I would appreciate that. Their research focuses on using chemistry and chemical engineering principles to design, synthesize, and utilize novel functional polymers, nanostructured materials, and their hybrid materials for the benefit of our society. Professor Zheng received his PhD on chemical and biomolecular engineering UCLA in 2012. His bachelor's in chemical engineering from Tianjin University in 2007, and his postdoc chemical engineering from Stanford University in 2016. Please help me welcome Professor Chen. Please, Professor Chen, go ahead.
Okay, thank you very much for introduction, and thank you for invitation. Good afternoon, everyone. There's one thing I want to do is I'm going to stop the video during my presentation. Then I will restart the video during the QA session to make sure the internet flows better, because during the quarter there's some problem when I keep the video on. So anyway, what I'm going to share with you is I think it's not only just a technical presentation. I hope we can invite some discussion for a societal issue that is related to sustainability. So what I'm particularly interested in materials for energy storage And so that is what I'm going to share with you today. So before I'm going to introduce the specific technique, I'm going to basically briefly cover what we are doing in our research laboratory. So we are materials focused group in the nanoengineering department and the chemical engineering program. So we synthesize materials, we characterize materials, and we make them into device, and we also care about the life cycle analysis and circular economy. So besides this, we also have a lot of applied research to try to solve practical issues. For example, in using batteries, we don't want to have any fire hazards or exposure issues. We want to design batteries that can last them more than 20, 30 years. And then we also hope to help astronauts and, for example, NASA to send satellites to provide a power in the space so that these batteries can tolerate very high temperature as well as very low temperature down to -60, -80, which your cell phone battery or laptop batteries cannot afford. But what I'm going to talk about is mainly the recycling issue or sustainability issue in topic 1. Okay, so one of the most important or critical driving force for designing batteries or recycling battery is to reduce the cost of batteries. So I want to use one example. This is the US Department of Energy's targets in the battery cost for the next few years. So right now we are somewhere around here, 2020. So this literature is slightly outdated, but the prediction is surprisingly accurate. So we are getting close to here, $120 per kilowatt hour electricity using battery storage. We're trying to push hard to get lower to like $80 per kilowatt hour. So in this case, we will have more affordable electrical vehicles. Tesla actually, Elon Musk has done very good job in reducing the cost of electrical vehicles, but still the cost is a little bit too high to make sure everyone can afford. We know Model 3 is more popular than Model S. One of the main reasons, I believe, is the cost. Okay, it's more affordable. So more than 50% of the cost comes from battery for EVs, for electric vehicles. So talking about the cost, the reason why lithium battery is so expensive or electrical vehicles are so expensive is because the materials we used for making these batteries are so expensive, okay? So I'm showing a few examples. The one highlighted in red actually is more expensive than others because you can notice from this chemical formula, so they use metals, transition metals, for example, lithium. Lithium is not transition, but is a very critical material. So lithium, cobalt, lithium, nickel, magnesium, cobalt. So, and lithium, nickel, cobalt. So the common feature for these materials is that we have to use lithium. We are using these transition metals such as cobalt and nickel, okay? So those metals are very expensive. I'm going to share you some numbers later on, but just try to highlight these materials at this beginning, okay? So in terms of cost, we are also facing a huge demand, okay? Face huge demand because I'm not sure if everyone has a basic concept of how many vehicles we are producing, for example, globally or just in US or in a specific country, okay? So I cannot do polling, but I want to give you maybe two seconds to think about how many cars we are selling, how many cars we are making, for example, last year. Does anyone have a number? Let me see. Okay. So yeah, I don't have a very accurate numbers, okay, average numbers, but okay, the scale, okay, the scale actually is around, okay, tenth of millions. For example, we have made around 70 million cars plus about 20 millions of trucks, okay, last year, okay. So this translated to a lot of, okay, a lot of demand if we are talking about electrification of transportation. For example, just simply replacing, we're not talking about half, just talking about 10%, okay? We're talking about almost, okay, almost 10 million cars using batteries. So these batteries, okay, will need a lot of metals, lithium metal, nickel metal, cobalt metal, okay? So this is survey that is done, not only actually Bloomberg done this, but US DOE also has done a lot of surveys. So basically, you will see the huge demand of electrical vehicles, but we also, okay, have to consider how to feed this demand, how to make batteries using limited resources, okay? So as extreme example, actually, I want to further highlight, okay, is talking about cobalt, okay? As I highlighted at the beginning, we need to use cobalt, okay? Even it's only a few percent in your car batteries, okay? If we compare the overall global reservoir of cobalt metal, okay, we only have a small amount, okay? So I have the numbers here. So identify the global reservoir of cobalt is around 7 million tons, okay? Talking about the steel, if you want to compare the steel, okay, global consumption of steel minerals is in the range, okay, is a range of about 1 billion tons, okay, 1 billion tons. But cobalt in total in the whole planet, okay, we are only able to identify 7 million tons, and we are already, okay, we have already consumed more than 1 million tons, okay. It seems to be a very small portion, but as we are pushing the bar of the production capacity of the electrical vehicles, in the next 10 or 20 years, we're going to use up all the cobalt. And the extreme knowledge here is that, okay, around 60% of cobalt is reserved in a small country, okay, in West Africa, okay, Congo, okay, Democratic Republic of Congo. 60% of cobalt is reserved in this small country, and this country is not developed country because they don't have infrastructure, okay, they don't have stable social and political environment. They are using sometimes, okay, in the news you can see, okay, child labor is a long-term issue. Things are changing, okay, things are changing, but they don't have very stable infrastructure. The efficiency of mining, environmental impact has to be seriously considered and revisited, okay? So that's why I said, when we talk about cell phones, talk about iPhones, we have to talk about batteries. When we talk about electrical vehicles, we also have to talk about batteries, particularly lithium-ion batteries. In making these batteries, we have to consider cobalt, okay? And then when we talk about cobalt, there are a lot of technical issues, but more importantly, we have social issues, okay, environmental issues, economic issues, okay? So the why we have to consider recycling, because if we have the battery to be made in a closed loop fashion, for example, if we open the cell phones, maybe older cell phones, you can see, okay, there's a very clear, okay, mark, okay, or I would say label. We try to recycle batteries at the beginning when we design the battery. One of the reasons is reduce cost, okay? Also want to reduce reliance on these critical metals or critical materials, okay? That means these metals refer to cobalt and lithium to reduce environmental impacts of manufacturing these batteries continuously by mining natural ores. As we just highlighted, we don't have so much of this kind of critical minerals, okay? We don't have a lot of cobalt in the whole planet. We have to recycle them, okay? To reduce the cost, reduce the environmental and the societal issue, okay? So the reason we can do this, okay, so I'm going to change the topic from this global picture to a specific technique, okay? So the reason we can recycle, well, we can think about recycled batteries okay? So there are many ways we can consider recycling. So from our perspective, we're going to take a different approach as what we call reversible chemistry or reversible process. So think about how you use your cell phone, how you use your laptop, right? So you charge your cell phone and use them for a few, maybe for a few hours or 1 day or 2 days, and then you use the electricity and then you charge them, okay? So the entire process of usage of your cell phone batteries and laptop batteries is reversible because you can charge them, you can discharge them, and you can do this for 1 year, maybe a few hundred times, or 2 years, right? So this is exactly what's going on from the materials perspective. So if you look at the batteries, so I'm just showing this diagram to mimic the materials. So the lithium-ion battery cathode materials, for example, they have such a layered structure, okay? So what I'm highlighting here in the blue color is basically lithium ions, okay? So lithium ions is the charge carrier, okay? So when you charge your battery, you are taking lithium ions, okay, from the materials, okay? And lithium ions will flow into from the external circuits to the anode, okay? This is a charging process. So in this way, you boost the voltage and you put charge start in the materials. When you discharge or when you use your cell phone to make the call, to read the news, then the lithium ions will flow back to the cathode, the voltage decrease, okay? And all the lithium ions flow back, and then your charge is used up. And then you can connect to your charger, and then you can do this process back and forth again and again. So this is exactly what we are using your cell phone batteries. And this is actually what is happening in terms of the materials, in terms of chemistry. You have many, okay, you are using the lithium ions to carry the charge, to carry the energy, okay, for you to use your cell phone and laptop repeatedly, okay? So this is why we call it reversible process, okay? So sometimes what is going on when you realize one day after maybe a year or a year and a half, you realize once you charge your cell phone for the same amount of time, like 4 hours, 3 hours, you can only talk for like 30 minutes, or your cell phone will die or powered off after a few hours. Compared with your fresh cell phone, you realize your cell phone is not powerful again anymore. The reason is that besides this simple lithium travel back and forward process, as time goes on, you are going to have some side reactions which we can identify using advanced characterization tools, for the microscope, spectroscopic techniques, to analyze the composition and structure change, okay? So we identified there's some chemical and physical degradation. So if we use this blue color to mimic fresh materials, and after a few hundred cycles or 1 year or 2, you will have a process happening we call degradation by inducing surface phase change, okay, to form new phases, which is something we do not want, which I highlighted here in this orange color, in this green color. So in original phase, we have this blue color, which is a very good layered structure, which we call layers because they have very weird orders, 1 layer, 2 layer, 3 layer, and then lithium stays inside. However, once we have this so-called spinel phase or rock salt phase, these are phases need to not follow this ideal layer structure. They have some lithium ions and nickel ions, they migrate into each other's position. They form new phases, and these new phases is not favorable for lithium ions to travel, to transport between 2 electrodes. So you are going to have a higher resistance. You are going to lose the amount of lithium that is going to be reversible, okay? So what we are doing here is by understanding this process, we are going to design a so-called regenerate process so we can reverse, okay, we can rejuvenate this surface phase, this orange phase and this green phase back into this well-ordered blue phase, okay, again, back to layered structure. So this is what we're doing. So we are making a lot of efforts after understanding this process and try to regenerate these degraded particles into regenerated particles, which will have exactly the same properties as your old materials. Okay, so in an experimental perspective, this is exactly what we are doing. Okay, so our starting point is, so if you taking an example of a lithium battery, most of them will look like this fashion. You have a bag or you have a case. Okay, you have these two strips. One is cathode, one is anode. You connect it in the electrical circuit. Okay, you do charging and discharging. Okay, using simple chargers, and then you can do this process like what you are using your cell phone, charging, discharging them for like 300 cycles, 500 cycles. And then this reaction, so-called degradation will happen, okay? So to test our methods, to demonstrate our recycling process, we get this degradation, we induce this degradation, and then we open the battery, and then we separate the materials. So actually your electrodes inside this pouch bag will look like this. They're all black. You cannot tell too much. They are all black, okay? Because we use a lot of carbon black to improve the conductivity of electrodes. And then we use some physical processes to separate materials, which we highlighted at the beginning, the metal containing materials, which is lithium cobalt oxide, lithium nickel cobalt, and the manganese oxide. And then we send this powder, which we call it black mass because they are black in color, okay? And then we send them to our regeneration process, okay? So in this process, we rejuvenate the composition and the microstructure, and then they become new particles, new materials that will enable us or allow us to make new batteries. And then we can put them back into cell phones or laptops. If we have the capacity to make a lot of batteries, then we can use them as fresh batteries. Okay, so this is how a simple process. Okay, so in this process, we can do two things. Number one, we do not let this material to go to the waste stream, right? Because we form a closed loop process. And the second thing we're doing is to reclaim the energy that is embedded into these particles. So what is embedded energy? That is something where I'm going to provide a little bit more details in the following slides. Okay, so I wanted to acknowledge the recyclers and the industry, actually the companies who are working on this recycling direction, recycling industry. We have a lot of companies. But if we look at this process, okay, most of them are doing so-called pyro or hydromagnetic process, okay, Umicore retrieve, okay, from Brown, Jim. So all these companies, most of them are doing this so-called hydromagnetic process or pyro process. But here at UC San Diego, we are doing so-called direct recycling, which is what I have just described in the previous slides, okay? So we also have a small spin-off company, which we call Unigrid, to commercialize some of the technology derived from our lab, okay? So what I'm trying to highlight, okay, to give you a better understanding how industry is doing the mining, how current industry is doing recycling, okay? As we pointed out, we have to, for every single cobalt atom, okay, we have to mine them from the natural resources, okay, minerals. So in the natural resources, the minerals contains less than 1%. So normally in the range of 0.3 to 0.5%, especially for cobalt, we do not have high abundance in cobalt. In most of cases, cobalt is mined, okay, at the same time as copper or nickel. So it's actually cobalt is a byproduct of nickel and cobalt of copper mining. Okay? That's why it is so hard to get them out of the natural resources. So anyway, let's assume we have cobalt and minerals. So we have to crush, okay, so these minerals and then separate them into small fine particles, and then we have to burn them, okay, to use high temperature and oxygen to burn them into oxides. And then we have to use a very strong acids together with oxidation agent, for example, sulfuric acids, together with hydrogen peroxide. to dissolve them into water, into a liquid. And then we add leaching agents, okay, complex agents and binding agents, and we add it to add a base to precipitate them. And then we purify them into many processes, okay, by many processes. And then finally, we got this high purity so-called precursor. This is a very common precursor to making cobalt oxide. Okay, this is cobalt sulfate. So I'm using 4 boxes to identify their typical process, but the entire process is actually very long. Okay, this is the primary mining process for getting cobalt from natural minerals. So talking about so-called pyro and the hydrometallurgical process. So actually they go through very similar operation processes. The only difference is that instead of using natural minerals, natural resources, now we have used the battery because we already concentrated cobalt from these low abundance minerals. We concentrate them into batteries. If we can put hundreds of or millions of batteries together, we can treat them as our resources. Then we do the same thing. We crush a battery, we separate different materials, plastic, metals, and oxides, then we burn them. And then we leach them using acids, and then we're using complexing agent and acid and the base to precipitate, and then we purify. The entire process is almost the same, okay? The only difference, again, is only the feedstock. Instead of using the natural minerals, we're using old batteries, which have higher concentration of this metal. So in talking about direct recycling, okay, so what we are doing, okay, is very different, okay? So we take the older batteries, we crush them, we separate them. However, in the next step, instead of burn them or dissolve them, okay, we are using this process we described previously. We send them to a rejuvenation or so-called regeneration process. Instead of getting very long process of unit operation, we are trying to heal, okay, or treat them to fix the surface microstructure and the composition. And then by the end of the process, we directly get these so-called cathode materials, which we can see we highlighted in red color, which is lithium metal oxides, instead of doing this precursor, okay? So in terms of total number of boxes, looks similar, but if you look into the details, there remains a huge gap from this metal precursor to this cathode materials or lithium battery materials, because we have to take this precursor to go through this dissolution, precipitation, mixing, sintering process until we can obtain these lithium battery cathode materials. So hopefully I use these slides to distinguish the traditional mining process, the current industry of pyro and hydrometallurgical process for recycling, okay? And then to highlight difference of direct recycling. So by doing direct recycling, we directly convert old lithium batteries to new lithium battery materials. So we don't have to go through this process, because for every single unit operation or chemical operation, we need to input energy. In order to input energy, we have to burn something, either coal or natural gas or nuclear power, okay? So this energy means embedded energy that I highlighted in the previous process, okay? That's why I said we not only claim materials, we also reclaim the embedded energy inside the materials that we have to spend to make them, okay? So that is a big difference, okay? So in the following slides, I just want to show you how we do this, okay? So of course, every process needs to be optimized, and we have in our lab, we have spent the last couple of years to not only invent, but also optimize the process to reduce the usage of chemicals, reduce the usage of water and energy, to make this process, so-called direct regeneration process, more efficient, okay, more efficient and cost effectively. So this is what we did. So we have these old materials and we send them to some reactor, and then we do some process, and then we make new materials. So this is very simple, straightforward. So this is more some data I want to show, but it's probably too much details. Okay, too many details. So what I want to show here is how to identify the process kinetics and then tell us how much time we need to regenerate not only the composition but also microstructure. So we treated different materials. So this is 3 different type of materials. When we say LCO, and this material is lithium cobalt oxide. So it's probably more popular in cell phones because this material is energy dense, it's very compact. So we use this mainly for cell phone batteries. And for NCM, N is nickel, C is cobalt, M is manganese. Okay, so talking about 111 is lithium, is nickel, cobalt, magnesium 111 ratio in the mole ratio 111. And by saying 5 to 3, that means their ratio changes to 5 to 2 to 3. And then definitely we eliminated the lithium, they will have lithium, okay? 1 mole ratio of lithium versus the entire metal. So these are just different metals in these cathodes. So for these 2 materials, we use them more commonly in electrical vehicles, okay? For example, in the next generation of Tesla, we use a different ratio, but for General Motors, Chevrolet Volt and currently Bolt, we are using these 2 materials for electrical vehicles, okay? Because nickel is cheaper than cobalt, okay? So we studied how much time we need to change the composition, because we talk about the degradation, the failing of your cell phone and batteries mainly due to the loss of these blue particles, these lithium atoms, lithium ions. So we have to reduce lithium, and we have to understand how much time we need to reduce lithium into the faded, the old materials. So we identify the very distant range. We need 2 hours, barely 2 hours to get all the composition back. And then we compare this with the materials. So this is how the particles look like in terms of NCM 111. And this is 111, the first row. The second row is NCM 523. So they all look similar. So we want to compare how this particle material microstructure as well as morphology, particle size, and distribution look like after our entire process. So this is very crowded slides, but if you see there's very little difference. The truth is that indeed there's very little difference because the particle size distribution is similar. Okay, the morphology are similar. Okay, this is actually further demonstrate that why we can do this so-called direct recycling, because your materials itself, maybe 80% of them are still good. We don't have to do a lot of harsh treatments to crush these particles to dissolve them into strong acid, because we spend so much time and effort to make them to form such a morphology. Okay, so which is something we should maintain, we should keep. Okay, so this is also the reason, the advantage, the rationale that we have to do direct recycling. Okay, so in terms of the chemistry, if you do not want to focus too much in terms of all the metals, and you just have to focus on the lithium composition, which I have boxed them. For both chemistry, both materials, I use them as an example, NCM 111, NCM 523. So this is pristine. You can imagine pristine means the batteries that you just buy, okay? You buy a fresh cell phone, you have a fresh battery, then they will have about 100%, which is 1.0, something like this is very close, 0.995 or 1.009. This means basically is 100% of lithium. After cycling, that imagine you have used a cell phone for like a year or a year and a half. So in your cell phone, if you open your battery and you do some testing and you can identify you lose about 23%. Okay, this is basically the reason that is responsible for the cell failure. Okay, so after our process, we try different process, different conditions, you can see, okay, the change of composition back to 1.0, 1.0, 1.0, 1.0, okay. So this basically gives you an idea that how we can basically regenerate the composition back into the desired composition that we have for fresh or for new batteries. Okay, so this is just something I think we can understand more easily. So in terms of this microstructure using X-ray diffraction, I don't want to talk too much, but just gives you a very general idea is that if you compare all these patterns, they look similar, right? This is because they are indeed similar. As I said at the beginning, after 300 or cycling or 1 year of usage of cell phone, there's very little change. Okay, all the change happens on the composition on the surface and the phase on the surface. That we can use a small amount of effort to basically shift them back. If you're looking at this is fresh battery, if you follow my laser point, my point that you have the position here after cell filling, your position shift to left. After our treatment, the position shift to right. So this position shift basically tells us we can regenerate, we can heal, okay? We can do some healing process to make old batteries, okay, become attain to new and fresh materials, okay? So we did them for different materials, NCM 111 and NCM 523. They share very similar feature, okay? So this is some performance which we can easily compare. So the black is the fresh materials, which will not have any treatment. So this accurate is the materials after a few hundred cycles of usage, they degrade, of course. The rest shows how we can recycle them and achieve the same performance. What we want to compare is these numbers on the y-axis shows the capacity, which means how much energy we have. On this right curve, I mean on the rest of the curves shows how much they can retain their charge or energy over a number of cycles. So the rest of curve shows how much power, which means how fast. The larger the series, the C numbers shows the faster cycling or faster charging rate. And this curve just describe their basic signature or electrochemical or charge storage behavior and charge release behavior. So we don't have to focus too much as the general audience if you do not understand a lot of electrochemistry, but just show you some of the curves to compare how we basically rejuvenate and regenerate these older materials to achieve comparable performance, that we can use them to make new batteries. We did test many different materials. So this is an example showing we can not only treat single material, we can also treat the mixed material. So again, this LCO is cell phone batteries. This NCM is electrical vehicle batteries. So because imagine we have an industry, we have a plant, we want to treat a waste stream that can possibly include a different batteries. So we want to see if we can use same process to treat mixtures. Okay, so if you cannot tell any difference, that is correct. Because again, there's not much difference because after our regeneration process, we can get materials after regeneration to achieve very comparable or the same level of performance if you compare the shape of the curve, compare the numbers, and compare the cycling trends and the values after 100 cycles, they show very similar properties, which means even doing mixtures, we can use our direct regeneration process based on the reversible chemistry principle to do recycling of battery materials. So this is process. We have a further development using new chemistry. Basically, I'm probably going to just talk about very briefly. So the purpose of doing this is to keep investigating new chemistry that we can use more cost-effective process, more energy efficient process. In this case, we use a pack mixture, which we can get rid of the pressurized reactor to do the recycling. Okay, so for the same process, similar process, we can treat similar materials. As we can see, we can treat very heavily degraded materials to regenerate the composition to achieve materials that will share the same same properties as your new materials after. For example, by this condition, we can achieve very good composition that will deliver a very good performance that can basically reach exactly the same level of properties as pristine. When we say pristine, that means new material. Okay, the rest two are materials that we have tested different recycling conditions using these new methods. Okay, so the rest shows how they behave when we look at the fine structures, fine properties during battery recycling, battery charging discharging process. So we have also thinking about how we can change the chemical nature from older materials to new materials. One example I want to compare is that we're talking about plastic recycling, right? So the industry are not doing plastic recycling very intensively and extensively. The reason because is that the plastics, for example, your plastic bag that you use for shopping, and the plastic that we use for toys, for home goods, these plastics are so cheap, okay? We have to spend a lot of time and energy to recycle plastics. So in the end, the recycling process is expensive, and the revenue we get is so low. So there's very little driving force for industry to do recycling, unless the government put a mandatory requirement for certain industry to do that. Okay, or customer will pay more price when we buy a new plastic products. We add the price on top of the recycling, on top of the on top of the intrinsic price to save some money for recycling industry players. So that is a limitation of doing recycling. The same thing for battery, that is for future applications that we are going to further reduce the batteries. So that means we are going to use less and less critical materials and cheaper materials. So what are going to treat low cost batteries? So we have to consider our process to be very robust and can change or can upgrade older materials to new materials. Same thing for plastics, okay? So in the end, we have to compare for future chemistries. There are a lot of materials that we have to consider, and some of them are very cheap. Some of them are more expensive. So no matter it's cheap or expensive, when we use them in very large scale, we are going to talk about not only kilograms or tons, we're talking about millions of tons or more than that, okay? So that means a lot in terms of resource impact and the environmental impact. So I'm going just showing a few examples in terms of their cost, okay? So here I promise to give you some numbers, okay? So in 2018, Cobalt has a big price. You can see here, Cobalt has been ramping up to a cost around $6 per kilogram, and right now is around $30 per kilogram. It's very expensive, okay? So even we replace the cobalt by more and more nickel, which is currently industry are doing. For example, Tesla is doing. We're talking about cobalt-free batteries or nickel, high nickel batteries. Still, nickel is not cheap. Okay, it's more than about $12 per kilogram of nickel. So we don't have a lot of nickel in the whole planet as well, like a cobalt. So every time when we see a lot of demand, for example, we have a rocket rise for certain products. For example, one day electric vehicles becomes so popular, everyone is using every household like today. Every house have at least 1 or 2 electric vehicles. What is going to happen? We're going to use a lot of lithium metal. We're going to use a lot of nickel, cobalt, and manganese. Okay, as we're talking about at the beginning, we only have one planet. We have very limited resources for all these critical materials, especially for United States. United States in total, for now, we only identified 55 kilotons of cobalt. Okay, That's very risky, okay, for us, okay, for the country, because we have to fight with Asian countries, with European countries to acquire these resources. Same thing for nickel. We have more nickel, but we don't manufacture them. We don't produce them, okay? There will be a lot of demand down to the years, okay? In the next 10 or 20 years, there will be a lot of industry issues. There will be a lot of competitions between countries to really meet, okay, the future requirements for customers, for our demand, for greener transportation, for electrical vehicles, for more cost-effective products, goods, okay, like iPhones, iPads, laptops, and electric vehicles. So this is going to be a huge, okay, technical challenging, and environmental and social challenge. So we have developed technologies to meet the demand. Okay, definitely, what we are doing here cannot solve all these problems. We have a future. We have remaining challenges. We have future projects to keep doing and think about cost, scalability, a lot of issues to be considered. A massive amount of work to be done. Okay, so but we have to think about. We have to start working on these problems before every household have 2 electrical vehicles in their garage, and after 80 years, they're going to retire and they have old batteries to be treated. Okay, we don't want customers to pay extra few $1,000s to be responsible for your old cars. Okay, so we have to develop a better technology to do them. Okay, to do this job. So this is something I want to share with you today. And then we have to design a lot of new technology and identify new science. And we need a lot of talents and resources to do this. So with that, I would like to thank for your attention. And at the same time, definitely thank for my team to do this. And if there's any question, I will be very happy to talk with you, to discuss with you, and welcome for your suggestions and comments for this type of kind of work. Okay, thank you.
Thank you so much, Professor Chen. Indeed, a very interesting subject about recycling. And now we can go to questions. If you would like to raise your hand, it's under the participants icon. And there you can click the button and raise your hand if you have any questions for Professor Chen. And I will unmute you as you are here on the list. Professor Chen, I do have a question for you. What's the percentage of batteries that we are currently recycling?
Okay, yeah, this is actually a good question. So we have talked about from country to country. So for example, in Europe, okay, European countries have taken actions much earlier, back to 2000s. They have a demand and they have a mandatory requirement for all these manufacturers to recycle at least 20%, and now it becomes 50% of batteries. So now the problem is that recycle does not mean regenerate, okay? So when we talk about recycle, if we talk about recycling other materials like plastics and papers, okay? So the collectors, they will carry your old cars, your old batteries to a certain warehouse. They store it. They keep it over there without doing anything because there's no mature technology. There's no profitable technology of doing that. So we recycle it, they haven't been able to really take advantages of these resources, which we call it urban mines.